Thank you very much, Giovanni, for inviting me to give this presentation. This is really very new work, and as you can see, it was done in collaboration. The experimental work was done by my group at Empa, particularly by Andra and Oz, the second and third author here on this talk. And the theory work, the micromagnetic simulations are done by Ricardo and Giovanni, and also partly by Dieter Süß. So we have already heard about the problems using Skyrion in racetrack memories. Although Skyrions have been identified as the ideal information carriers for racetrack memory applications, there are various problems connected with that, and that hinders the realization of this system. In a Skyrion racetrack memory, the information is usually stored by the presence and absence of Skyrions, and we heard today that it could also be stored by a Skyrion and other objects. Now the issue is that the Skyrions must move along the track, so you must suppress the Skyrion Hall effect, as we heard many times, and we also have to keep the distance between the Skyrions, and this is a challenging task. So for the first problem, a solution or a potential solution has already been presented by Vincent, and you can also read their excellent paper. It's about coupling Skyrions, ferromagnetic Skyrions, anti-ferromagnetically together, and that annihilates the spin Hall effect. But how do you keep the distance between the Skyrions? That's really a challenging thing, particularly because the Skyrions, they need to be pinned at certain sites, and they need to be moved from one pinning center to the next. So you need to apply current pulses, and unfortunately, they can be too short, so the Skyrions do not really move, or they can be too long, so the Skyrions move like two pinning sites, whatever produces these pinning sites. So there will be a large bit error, and this has been pointed out in theoretical work by Dieter Süß. And he has not only pointed out that the bit error rate, for example, in a random access memory needs to be smaller than 10 to the minus 9, and in hard disks it's even smaller. So also in a Skyrion racetrack, you must have a bit error rate smaller than 10 to the minus 9, which in present materials can only be achieved, if the Skyrion diameter is large, so it averages over many pinning centers. Well, that's not really what you want to do, to have such a large magnetic object. So Dieter has already proposed the solution, and the solution is to have two layers carrying Skyrions, one layer here at the bottom that carries a Skyrion chain, which is a periodical chain of Skyrions. So the distance between these Skyrions is very well defined, and the chain moves as a whole chain through the device. And then to write the information, you can either put an additional Skyrion in this top layer or not. And because these Skyrions are coupled via their stray field, the chain at the bottom, which has a regular inter-Skyrion distance, moves along the bits that are given by either having a Skyrion or have no Skyrion. And Dieter could show that by this principle, you can lower the bit error rate substantially, and that may be a solution for a future device. But how do you realize this in the experiment? Well, there has been very nice work done by Zheng et al., published in the Nature Nano paper in 2018. And they proposed that you could use tubular Skyrions that you see here and chiral bobbers, which are basically something like half a Skyrion, or only existing at the top of their single crystalline material. And they have not only proposed this, but they have shown that in iron germanium single crystals, in small single crystals, at 95 Kelvin, using electron holography, they could really show that such tubular Skyrions and Skyrion bobbers exist, and maybe these could be used to move along the racetrack. The only technical problem here is that this material has a very low TC, which is actually around room temperature, and these images where the bobbers and the tubes occurred was at 95 Kelvin, so that's far away for an application. And also the processing of single crystalline materials may be very challenging for a real application. So basically we came up with a thin film based solution. And actually Christos probably likes to see this. We took basically his system consisting of an iridium, iron, cobalt, platinum multi-layer, and we have learned that we have additive DMI and negative DMI at this interface, And actually positive DMI of this interface, but because it's flipped the other way around, it's also negative. So basically both interfaces give the same sign of DMI, and you get a very large DMI, as Christos has already shown here, this beautiful MF images. The first step we have done is we have grown his systems, but not with 20 repeats. We just grow 5 repeats and also 1 repeat and 3 repeats, but I'm not showing you the results because we later used a 5 repeat sample. And here you see a sample consisting of iridium and then iron 0.2 nanometers, cobalt 0.6, and platinum times 5. And you see the Skymion density, and here you see 2 MFM images overlaid, so you see which Skymions are pinned and which move. And the Skymion density is very similar to what Christos found. I put here his image with the same scale as ours. But then, of course, you can modify, as he has also done, you can modify the thicknesses, and you can obtain extremely high Skymion densities in this material. And you can also modify the cobalt layer, which when we make it a little thinner, we get a slightly higher density than here. So that's the base of our system, using this system to generate the Skymions. Then we use rare earth, amorphous ferrimagnetic rare earths. We use these materials, we have studied them over years, and they are very convenient because you can tune the magnetization by the rare earth to 3D ratio, but you can also tune the anisotropy by replacing some of the terbium by gadolinium. And you can do this, well, more or less independently. Here you see a few VSM loops recorded in the in-plane and out-of-plane geometry to assess the anisotropy of these materials. And first, what you see here, by reducing the 3D element in the composition here, we can down-tune the magnetization. So we could go further actually if we put the compensation point to room temperature, then of course we will have 0 magnetization. So we would have something like an antiferromagnet or comparable to an antiferromagnet. Then on the, well, the anisotropy remains actually constant if we have sufficient rare earth in the material. So here we have just 5% of terbium. The anisotropy is actually negative, so the system is in plane. But here it goes out of plane if you put a little more terbium. And then you see, although we reduce the 3D element, we keep the anisotropy at about the same level. So that means you can tune the magnetization without affecting too much the anisotropy. Then you can go this direction here, and here you can see that we can down tune the anisotropy by increasing the gadolinium content. Now these materials can be grown as amorphous alloy layers or also as a multilayer, and here you can change the ratio by the thicknesses of the rare earth and 3D elements. Now we have done a lot of work, and you can find, for example, this one already recently published, and we have done a lot of quantitative MFM and micromagnetic modeling. So that's really represents state of the art in micromagnetic modeling, and then understand the very complicated hysteresis these 3D materials have on top of the rare earth amorphous ferrimagnets. Now, the structure we used here is basically the structure proposed by Christos, right? These iron, iridium, iron, cobalt, platinum multilayers, which we call the Skymion generator layers, which we put at the bottom, a 5 repeater of that, a 5 repeater at the top, and in the middle we put this amorphous ferrimagnetic alloy layer as shown here. And look what we get at room temperature if we do MFM. This MFM has been done in vacuum. We use cantilevers that have an extremely high quality factor, between 200,000 and a million. So we are super sensitive to detect these Skymions. Now we have 2 different kinds of Skymion, 2 Skymion phases, these intense ones and a lot of the weaker ones. So let me show you what happens if what is the magnetic field evolution. So you see here an image taken at 0 millitesla. So we have maybe a few Skymions here, but we have predominantly this stripe domain phase. And then if you increase the field, of course, the stripe domains, they are erased, and we get more and more Skymions. And as I said, we have 2 different Skymion phases here. Now, if we further increase the field, then of course the Skymions will die out, and you see that the part of the strong Skymions will be converted into the weak Skymions. So let me highlight this a little bit in more detail. So what we see here is a plot following this black skyrmion here. That is a strong skyrmion in low fields, and then eventually between 160 and about 180 millitesla, 177 millitesla, we have converted it into a weak skyrmion. Here is another example. That's the blue skyrmion here. That converts into a weak skyrmion a little bit at a little bit lower field, but there is a jump in intensity here. Whereas if you compare it to an initially weak skyrmion, well, that also gets a little bit weaker in contrast, but that's well understood by the size of the skyrmion that shrinks if you apply a field. Whereas here, also there is a little loss in contrast, whereas the size of this intense skyrmion also shrinks, but then there is a sudden jump to this weaker contrast level. So clearly, we have two distinct skyrmions coexisting, and obviously the skyrmion radius also shrinks continuously with the increasing field, but there is this abrupt transition from strong to weak skyrmions. So the question is, in our super heterostructure multi-layer sample, in which layers do these skyrmions exist? And to answer that question, we have first done an experiment and then later on micromagnetic calculations. So what we have done, we have grown decomposed samples, so samples consisting of parts of our heterostructure. Here only the skyrmion generator on the ferrimagnet, two skyrmion generator layers, a skyrmion generator interrupted by a non-magnetic tantalum layer of the same thickness than in our usual heterostructure sample where we have the ferrimagnet here. And then we do quantitative MFM, quantitative in the sense that we developed a very good distance control method, and actually the tip never touches the surface, so the tip stays the same. You can do experiments over half a year, and the tip is always the same, and we have perfectly the same tip sample distance, which allows us to compare these images. And if you do that, so if you evaluate these skyrmions indicated by the blue crosses here, we can fit these skyrmions, we fit them by a simple 2D Gaussian function. So here are the measurements, and here you see the fits. And if you look at the intensities of these skyrmions, then we find, maybe a bit small, but we found about 0.3 hertz of frequency shift for a single skyrmion layer. If you put the single skyrmion layer on top of the ferrimagnet, not much changes. There's a little bit of weaker contrast. If we double the thickness of the skyrmion layer, we more than double the contrast as seen here, and also becomes apparent from the pictures. But then if you do this sample, where we have two skyrmion layers with interrupted by a tantalum, you see we get, again, about the same contrast as for two skyrmion layers. It's just a little bit weaker. But what is remarkable, that the contrast of these skyrmions here, which of course only exists in these skyrmion layers, not in the tantalum, is very comparable to the contrast we have in our heterostructure. So we can say in our heterostructure, the weak skyrmions that we have here, they actually correspond to skyrmions that only exist in the top and bottom skyrmion generator layer, but not in the intermediate ferrimagnetic layer. So you see, these are the weak ones, which correspond very well to these, and the strong ones are considerably stronger. So our conclusion from this experiment was that the weak skyrmions are actually incomplete skyrmions existing only in the top and bottom layer. So very reminiscent to the chiral bobbers found in 2018 in iron germanium at low temperatures. This is at room temperature. The strong skyrmion are actually the tubular ones penetrating through all layers. So we need to understand the contrast. And understanding contrast is actually not so simple, because the contrast is actually 81% stronger if you compare the tubular to these incomplete skyrmions, but the length of a tubular skyrmion is actually only 30%. So how can we explain let's say the 80% stronger contrast? Well, probably the radius is larger. But if you look at the images and if you do the Gauss fitting, you actually found pretty much the same radius. But this may be attributed to the MFM, which is performed 21 nanometers above the topmost magnetic layer. And of course, the stray field widens up, and so basically you end up with the two skyrmions looking almost the same apart from their very distinct contrast. So clearly, micromagnetic modeling is needed. And here the results done by Ricardo and Giovanni So basically we have two initial states. An initial state 1, where we impose skyrmions only in the bottom and top skyrmion generator layers, but not in the ferrimagnet here. And then we let the system relax, and you see what happens is actually quite interesting. The skyrmion radius enlarges a little bit, and in the topmost ferromagnetic layer of the bottom skyrmion generator layer, the skyrmion actually vanishes. It's suppressed by the strong coupling to the ferrimagnet, which is in a homogeneous magnetic state. Here you see the cross sections, right, with the skyrmion radius reducing somewhat towards the outer surfaces. And as expected for the negative DMI in this system, we have a clockwise orientation, which is actually the same for all layers here. Now let me relax the second initial state, where we have a skyrmion in the ferrimagnet. And if you relax this one, we get a totally different result. First, the skyrmions are very much larger. And then there are a lot of interesting details here. First of all, we have a skyrmion in the ferrimagnet now. And we have also a skyrmion in the topmost of the bottom skyrmion generator. So here, you see the radius is much larger here than we had it over here, which of course will explain the much stronger MFM contrast. Now, notably, the chirality of the bottom layer, which was clockwise here, has changed and becomes counterclockwise. And we attribute this to the flux closure here, which lowers the magnetostatic energy. And the flux closure just doesn't happen here because the skyrmion is so small, and that external field is small anyway because of the small size. Now let's look at some details. What is very, very interesting is that in the ferrimagnet, we actually attributed, we didn't measure, we attributed in the simulation a DMI of 0 plus 0.8 millijoules per square meter. And if we do that, obviously we get here a skyrmion which should be counterclockwise. And you see the arrows here, they're pointing outwards, so we have a counterclockwise orientation of the walls here, whereas we have a clockwise orientation in the bottom and top skyrmion generator layers with a negative D. But what happens at the last ferromagnetic layer here, that skyrmion here is actually frustrated. It doesn't know, does it want to take the clockwise chirality of the skyrmion according to the negative D, or because it's coupled to this one, which has a counterclockwise chirality, it decides to go into a state that can be described as a Bloch skyrmion with the magnetization running around inside the domain wall. Now, it is also interesting to study the radius of the skyrmion as a function of their position in the layer, and that's plotted in this graph here. So basically, the bottom skyrmion generator layer, which consists of 5 repeats of this iridium, iron, cobalt, platinum multi-layer. So you see the skyrmion is small to the bottom surface and then enlarges toward. Here you see there is no skyrmion in the 5th layer. It's actually suppressed if there is no skyrmion here in the ferrimagnetic layer. And in the top skyrmion generator layer, again, the skyrmion radius becomes smaller towards the top surface. Now, if we have the initial state 2, where a skyrmion is also enforced in the ferrimagnet, and then we let it relax, the skyrmion remains in the ferrimagnet. And you see here that the skyrmion radius here, the average radius, is considerably larger than that if you have only skyrmions in the top and bottom layer. And the skyrmion radius actually in the ferrimagnet is somewhat smaller than here in the ferromagnetic layers. And remember, at this interface, through the strong coupling, through the platinum, we get frustration. So this skyrmion is actually a Bloch skyrmion, whereas these are clockwise Neal ones, and these are counterclockwise Neal skyrmions, and here we have again clockwise. Now it is interesting that we have to attribute a DMI to the ferrimagnet here. And we know actually there is a DMI because we have a platinum layer here at the interface, and then we start with the cobalt layer before we start with the ferrimagnet, right, that contains a lot of cobalt. So we are expected to have a positive DMI that may be somewhat smaller than in a nice crystalline system. So that's why we decided to give it 0.8 plus 0.8. Now, we studied for other values of DMI. So if we reduce the DMI of this interlayer, then we get no skyrmion. So here, even if we impose a skyrmion in the interlayer as an initial state, it vanishes if you let the system relax. So there is a critical size of the DMI needed in the interlayer that it can support a skyrmion. Now, it doesn't matter so much which sign this DMI has. It works for positive and negative, but you get a larger skyrmion if the sign of the D, if they are the same, if they're opposite signs, actually they're a bit small. So how do we explain the contrast in MFM? Well, we explain the contrast in MFM. That's the spin texture that we have for the incomplete skyrmion, for the tubular skyrmion. And what you see here is the stray fields calculated 21 nanometer above the last magnetic layer. That's where we did the MFM. And the stray field intensity, so the Z component for the stray field, actually has an 81% ratio between them. And it's exactly the same as we found as a delta F contrast in MFM. So it is very clear that the MFM results agree very well with the theoretical, the micromagnetic simulations done here. And that brings me to the conclusion and summary. I've shown you that in this complex tri-layer heterostructure sample, where we have a skyrmion generator layer here at the bottom and at the top, and this ferrimagnetic interlayer, we can have two distinct skyrmion phases at room temperature. And this is very crucial. I have also shown you that we can convert the tubular skyrmion to an incomplete skyrmion, that we need a DMI to stabilize the skyrmion in the interlayer. I did not show you that, but depending on the anisotropy of the interlayer that we can tune with the gadolinium terbium ratio, we can tune how much of these intense skyrmion, we can tune the ratio between the complete and the tubular and the incomplete skyrmions. So the tubular skyrmions have a larger radius, and possibly in a later device, we can discriminate between the tubular skyrmions and the incomplete ones by a Hall sensor. That seems to be feasible. And I think with that system, we can solve the second problem of a racetrack, namely that we can now form a chain of tubular and incomplete skyrmions and move them through the device and keep the distance between the skyrmions. And this is also a first step towards more 3D data systems, data storage system like Matthias Chloe has shown, right? I mean, here we have 3 different functional layers, and I've shown you that we can modify where these skyrmions occur. And with that, I would like to thank you for your attention.